Hey everyone, in this video we're going to continue talking about indefinite integrals, and in this particular video the net change theorem. So this is section 5.4 from our textbook. So the first thing that I want you to do is think of a real life example that illustrates the difference between displacement and distance traveled. So go ahead and pause and think of what does that mean? What does displacement mean versus distance traveled? And then when you're ready, unpause and then I'll show you my example. So the example for me that came to mind was hiking. I enjoy hiking, and this is one of my favorite trails to hike, especially when I am training for a trail run of sorts. And so what displacement means is essentially when you start. So if you look at this green and black little dot over here, that is the start of the trail. And so you can then go along on the trail, and this is a loop trail, so then you go back and you end up where you started at the trailhead. So that will be, in this case, your displacement will be 0, because from where you started and where you ended is the same spot. So the displacement will be 0, but noticing the information for this trail, this is a 4.5-mile loop trail. And so the distance traveled, so when I go hiking, or running when I'm preparing for a trail run, the distance done will be 4.5 miles, yet the displacement is 0 because I started and ended at the same place. So displacement refers to how far are you from where you started, whereas the distance traveled is the entire path taken, so the total measure of the distances. And so this is where the net change theorem comes in handy. And so what the net change theorem is, it essentially tells you that the integral of a rate of change is the net change. So let me write that out. And using the fundamental theorem of calculus, we can write it more in using this definition. So the net change theorem, essentially the integral of a derivative, right, of a rate of change gives you the net change. So essentially the fundamental theorem of calculus is giving you the net change. Now, when we talk about the distance, that's a little bit different, because how do I integrate something, right? And then especially something that goes backwards. So when I say backwards, going back to this hiking trail, the map, right? Notice that as you hike one way, when you get to this little point down here, then you hike back. So back to the starting point. So you don't necessarily back in the same way you came, but you go back towards the starting point. So in thinking about the area between the curve and the x-axis, that will mean that you are traveling underneath the axis, right? So going the reverse way. So if I was going to draw my velocity, for example, in this hike, it would look something like this, right? So this is me starting out and then coming back. So this is negative. The velocity is negative because I am on my way back. So that's what a negative velocity would be. So then the reason I drew symmetric is so that then when you look at the area under here, right, that's my distance traveled. And then this is the distance traveled on the way back. So then this will be the start at the trailhead. And then this will be my end at the trailhead. So hopefully this gives you an idea of like why, in this case, my displacement will be 0. Because, right, the area, this distance will be the same as that distance, because the distance is the integral of my velocity. And so that will be the displacement. Whereas what about the distance traveled? The distance traveled will have to be, I have to add that area. So it'll be my area 1. I'm going to call that A1, and then this will be A2. My distance travel will be A1 plus A2. But A2 is negative, so I'm going to have to do the absolute value of the function there. So that's how we're going to find the distance traveled. So then we're going to say that the distance traveled then is going to be the integral from A to B of the absolute value of my rate of change. So back to my supposed velocity here, what will be the absolute value of this? The absolute value will be, well, whatever's positive stays positive, but whatever's negative becomes positive. So essentially then I'm going to have, see if I can try to recreate it the best that I can here. So I'm going to have that, but now instead of going underneath the axis, right, the absolute value says I'm going to come back up. And so pretend those are the same. And so this is now the area. So I'm going to have my A1, right, plus A2 is now positive. So this is my total distance travel. So for the total distance, you need the absolute value of the velocity. So that's the important part. For the displacement, you just do whatever the curve is, you do the integral from A to B of the velocity function, and that's it. But for the distance travel, you have to take anything that's under the curve. That means that whatever it's moving is traveling backwards, right? So then you have to then take that into account. But if you want just the distance, then you have to make that a positive value so we can find the area. So the distance travel is the absolute value of the rate of change, whereas the displacement is just the integral of the rate of change. All right, so let's try an example. So let's start with this example. So we have the velocity function is given in meters per second. So this is a rate of change. As soon as I see meters per second, I have a rate of change. So the velocity function is given for a particle moving along a line from t equals 2 to t equals 4. So since it's meters per second, that's t equals 2 seconds and t equals 4 seconds. Find the displacement and the distance traveled by the particle during the given time interval. So here, let's remember what we just said. The displacement is the net area. So it's just going to be the integral from A to B of the velocity function, that rate of change. And the distance traveled is the absolute value of that rate of change of the velocity function. So in this particular example, the displacement is the easiest one to find. So displacement, we're just going to say is the integral from A to B, so from 2 to 4 of v of t. So we have the velocity, so it'll be t squared minus 2t minus 3 dt, and we just find the antiderivative here. So that will be t cubed over 3 minus t squared minus 3t from 2 to 4. And now use the fundamental theorem of calculus to plug in. So we always do, right, f of b, the top limit, minus the bottom limit, f of b minus f of a. And so now let's plug it in. So you're going to have 4 cubed over 3 minus 4 squared minus 3 times 4, and then minus, and make sure you use parentheses here when you plug in the 2. So 2 cubed over 3 minus 2 squared minus 3 times 2, and then figure out what that is. And so going back to the fundamental theorem of calculus, this is your f of 4 minus your f of 2, right? F of b minus f of a. And doing the math here, so this is what, 64 over 3 minus 16 minus 12, and then minus, I'm going to keep my parentheses there, so that's 8/3 minus 4 minus 6. And then if you want to get rid of the parentheses, distribute that negative in there. And what's this? Minus 28, and then minus 8/3 plus 4 plus 6, which is really plus 10. So let's see, what's 64 minus 8? 64/3 minus 8/3. Since those already have the common denominator, I'm going to combine those, which will give me 56/3, and then negative 28 plus 10 really is minus 18. And so here, if you want to get a common denominator, we certainly can, and then get a final answer. So common denominator is 3. So what is this? 56 thirds minus 54 thirds, which will give us 2 thirds. So that will be the displacement. 2 thirds what? What are our units? So meters. The velocity was given in meters per second, and remember when you do the integral of the rate of change, you get the integral velocity is distance, so this is the distance. So the particle moved 2 thirds meters from its starting position. Now what about the distance? So for part B, the distance, this is a little bit harder because we have to find the absolute value. So the distance is the integral from A to B of the absolute value of the velocity, dt. So in this case, it's going to be the integral from 2 to 4 of the absolute value of our function, which was t squared minus 2t minus 3 dt. But this, we can't just integrate it because I have the absolute value in there. Remember, absolute value, you have to split it into two cases, the positives and the negatives. So let's take a look at the graph of this and see what it looks like. So the graph of this function looks like this. So it's a nice parabola. And so from here, we can see why our displacement is the way that it is. We're on the interval from 2 to 4. So we're looking at the area here to 4, so the area here. So notice that the area from that x-intercept to 4, which is that 3, from 3 to 4 is bigger than this one. So that's why we get the 2 thirds meters in displacement. But what about the total distance? The total distance is, I have to take the absolute value of this. So that means that whatever is negative, so in the parabola, right, from here, from what's that, -1 to 3, the parabola dips in the negative, so we have to bring that up to do the absolute value. So when I reverse this, I would put it up here and try the best that I can to bring it up, right? So then this will be the absolute value of t squared minus 2t minus 3. So together, right? So if I trace it, pretend that I'm tracing it, then this will be my absolute value function for this rate of change. So now when I look at the distance traveled, I'm looking at the area here plus this area. So that will be the distance. So how do I get the equation of this part, right? So remember the absolute value, going back to the definition of the absolute value of x, is a piecewise function. It is x when x is greater than or equal to 0 and negative x when x is less than 0. So for our particular function, right, our f of x, or v of t in this case, then what is this going to be? So that's going to be a piecewise function v of t when, and we have to find the places where essentially this goes negative, and then negative v of t, or sorry, the places when t is positive is going to remain positive, and negative v of t when the t's are negative. So from -1 to 3, so when t is between -1 and 3 is going to be negative v of t, and the other places is going to be positive. So where is it? From -infinity to -1 union, and then the other place will be 3 to infinity. That's going to be when it's the positive, we just leave the function alone, or negative of the function between those values. So because our integral goes from 2 to 4, so 2 is before that point of intersection, we're going to have to split up this integral. So the distance traveled, which is the integral from 2 to 4 of the absolute value of v of t dt based on this is going to be the integral from 2 to 3, because based on the graph, that's where we cross the axes. That's when you go from negative to positive. So the integral from 2 to 3 of negative v of t. And then plus the integral from then 3 to 4 of just v of t dt, right? Because that's where it's already positive. So when it's positive, we want it to stay positive. When it's negative, we want to bring it up. So you do the opposite of that. So that's what this will be. So our total distance travel then will be the integral from 2 to 3 of negative our v of t, our function. So t squared minus 2t minus 3 dt plus the integral from 3 to 4 of the function as it is, t squared minus 2t plus 3 dt. And now we can integrate it. I don't need the integral symbol if I'm going to integrate. So I'm not going to distribute the negative until the very end. It's up to you. So I'm going to just leave it out here negative, and I'm going to take the antiderivative. So tq over 3, we already did this antiderivative in the displacement problem. And we're doing this from 2 to 3, and then plus tq over 3 minus t squared. Oops, that should have been a minus 3 there. Minus 3t, and this one is going from 3 to 4. And so let's evaluate it. And it will look very similar to what we already did with the displacement. It's really just that this part, because we have that negative there. So let's plug everything in and simplify. All right, so once I simplify, I get 4 as my final answer. So the total distance traveled by this particle then is 4 meters. So that will be the total distance traveled, whereas the displacement was just 2/3 meters, right? So that means that the particle is traveling backwards, and then it goes the other way, or it's traveling one direction, I should say. It travels one direction, and then it turns around and then it starts going the other way. But it goes further in one direction than the other, so it doesn't end up at its original starting point. Hence, the displacement is 2/3 meters. So it's 2/3 meters away from where it started, and then the total distance traveled was 4 meters. So hopefully that makes sense. So that's kind of going back to my hiking example, right? If I hike and start at the trailhead, when I go and come back, my displacement is 0 because I ended where I started, so my displacement didn't change, but the distance travel in this, if I go to this trail, it will be 4.5 miles. So that's very different. So displacement is very different than distance travel. And so the formulas to remember here will be the displacement is the net area, which is the integral from a to b of whatever velocity function you're given. The distance traveled is the integral on the interval you're given of the absolute value of the function. Now here, I gave you the graph of the function, but what if you don't know what the function looks like? How can you still do it? And the way to do that is, notice that we were able to find the absolute value by noting the zeros of the function. So without the graph, what I can do is find the zeros of the function and then see how it lands with my interval. So without the graph, let me write that. So in our case, our function was t squared minus 2t minus 3. So find the zeros of the function means set it equal to 0 and then solve. So this factors into, let's see, two numbers are multiplied on -3 and up to -2. So that will be t minus 3 and t plus 1, which tells us then that t is equal to 3 or t is equal to -1, which we saw on the graph. So that means that the graph crosses at -1, touches 0, and at 3. So the question is, right, our interval is from 2 to 4. So we want to know, what is the function doing here? Is it negative at any point? So just pick yourself test point and see. So between 2 and 3, put in t equals 2.5 into the original function and see what kind of value you get. So this will be 2.5 squared minus 2 times 2.5 minus 3. And what you'll see here is that you're going to get a negative number. So that means like, oh, so then my function is negative there. So when I take the absolute value, I'm going to have to do from 2 to 3, I'm going to have to split it. So it'll be negative v of t here for the absolute value. And then here, plug in something between 3 and 4, t equals 3.5, and do the same thing. And what you'll see is that it's greater than 0. So then the absolute value will be, where it's negative, you're going to do negative v of t, and where it's positive, it's going to stay positive, right? And so that's how you will do it without the graph. So let's try another example, and we won't use the graph on the next example, just to practice. Okay, so here's our next example. So here the acceleration function in meters per second squared is given, and the initial velocity for a moving particle along a line. So find the velocity at time t and the distance traveled by the given interval. So let's remember that the well, first the velocity. So the velocity is the antiderivative of the acceleration function. So we can find that. And then the distance traveled, this one isn't asking us for the displacement. So it's just asking for the distance. The distance traveled is the integral from a to b of the absolute value of the velocity function, right, of the rate of change. So we need to first find the velocity function. So I know the velocity is the antiderivative of the acceleration. So let's find the antiderivative of that. So it's going to be the antiderivative of our acceleration function. So 2t plus 3 dt. And when I integrate that, I get t squared plus 3t plus c. I am not doing yet this on the interval from 0 to 3 because that's to find the distance on that interval. Here I'm just trying to get my hands on the velocity function. But we are given an initial condition that v of 0 is negative 4. So that means that when t is 0, the velocity is negative 4. So we can put that in. So that means that then I'm going to have negative 4, right? The velocity is equal to 0 squared plus 3 times 0 plus c. So that just really tells me that c is negative 4. So our velocity function, so therefore v of t is t squared plus 3t plus c, but c is negative 4, the initial velocity. So this is now our velocity function. And now we can try to find the distance. And I know I didn't ask for displacement, but just to practice, right? If, big if here, if asked for displacement, what would you do? The displacement, then you just do the integral from a to b. So our interval was from 0 to 3. So if the displacement, then will just be the integral from 0 to 3 of the velocity function, t squared plus 3t minus 4 dt, and then you would solve that. And whatever numerical value you get there, that's your displacement. So the distance is the harder one, because for the distance, we have to do the integral from 0 to 3 of the absolute value of our velocity function. And I said we were going to do it without using a graph. Well, without providing the graph first. So that means, but you probably want to have an idea what the function looks like. This velocity function is a parabola that's going upwards, right? So it's going to look something like that. So we want to see, okay, what portion of the parabola then falls below the axis, and does that happen during our interval? So find the zeros of this function. And so that means set the function equal to 0. And let's see. So two numbers are multiplied by negative 4 and then up to positive 3. So that will be t minus 4 and, oh no, t plus 4 and t minus 1. Does that work? So that means t equals -4 or t equals 1. And so notice that on our interval 0 to 3, 1 is on that interval. So t equals 1 falls in our interval. So we want to see, okay, from 0 to 1, what's happening, and then from 1 to 3, what's happening. So on 0 to 1, what is the function doing? Is it positive or negative, right? Is v of t positive or negative? Why do I need to know that? Because if it's negative, then the absolute value tells me to do negative v of t, right? And then on 1 to 3, same thing. Is v of t positive or is it negative? Because we want to know how we're going to treat it. So pick a value like 1/2. Well, I know it's going to change, right? So probably on the second interval, it's easier to test. So I'm going to test t equals 2 into v of t and see what kind of value I get. V of t is t squared plus 3t minus 4. So what happens when you plug in 2 in here? So v of 2 will be 2 squared plus 3 times 2 minus 4. So that's going to give me 6, which is greater than 0. So then I know that in this interval, it's positive. So absolute value of positive stays positive. So then that means that in this interval is negative. And so for negative, v of t, I'm going to have to attach the negative to it, right, to make it positive. So this parabola, and if you wanted to quickly look at a graph, let's try to do that. So that means that this parabola has x-intercepts, we said, where at -4 and at 1. So it's going to look like -4 and 1. So that's where the parabola touches the axis. And we already know, because it's a positive t squared, that it opens upwards. So if I try to draw this parabola, it's going to be underneath the axis here, and then it goes up. And we're looking at the interval we're from 0 to 3. Was that our interval? Yeah, from 0 to 3. So not drawn to scale here. So you're going from 0 to 3. So you're looking at this area. That's for the displacement, but for the distance, then this part that's underneath the axis, I need to bring it up and do that, right? So if we did the absolute value of this function, so this one, let's call this one our v of t. And so then if I take the absolute value of this function to say the absolute value of v of t, then I'm going to try to draw it here. Then it's still going to cross the axis at -4 and at 1, but whatever's positive will stay positive. So from -infinity to -4, and then from 1 to infinity, that will be positive. But then this part that's under the axis, right, has to then come up. So this will be the absolute value of the velocity function. So this is the absolute value of v of t. And when I'm looking at the distance traveled from 0 to 3, I'm looking at now this area. So from 0 to 1, and then from 1 to 3. So I need 2 integrals for that. So let's go back to it. So the distance, right, then is going to be the integral from 0 to 1 of, I had to bring this part of the function up, so that means I put a negative in front of it. So negative v of t dt, and then plus the integral from 1 to 3 of just v of t dt. And now plug in the actual function. So our velocity was, so I'm going to put the negative there, t squared plus 3t minus 4 dt plus the integral from 1 to 3 of Now we don't need that negative there. We just do the velocity function. So t squared plus 3t minus 4 dt. And then we integrate both of them. And well, this is going to be the same, but here we have to keep in mind that we have that negative there. So when we integrate, I'm going to have that negative still out there, and it's going to be t cubed over 3 plus 3t squared over 2 minus 4t. And this I'm evaluating from 0 to 1 plus then t cubed over 3 plus 3t squared over 2 minus 4t. And this we're integrating from 1 to 3. And then evaluate and simplify, and that will be our total distance traveled. So let me do that and see if we get the same answer. So after you plug everything in and keep track of your negatives, then it reduces to 89 over 6 meters. So that will be the total distance traveled. It'll be interesting to actually do the integral for the displacement and see what you get, right? But notice based on the graph, it again looks like the portion of the graph that's under the axis is smaller, right? The area there is smaller than the area that's above the axis. Although I may not have drawn this to scale, so maybe a more accurate graph will help. But so that kind of helps us see if you can get your hands on the graph. It helps you visualize the displacement, right? The net change, the net area is the sum of the area below the axis and above the axis. So below the axis just means that the velocity is negative. And then the total distance traveled, you have to do the absolute value of the velocity. So oftentimes we kind of hope, right, that our velocity is always positive, but that's not usually the case. And so we have to figure out where does it dip below the axis on our interval. So our interval here was 0 to 3, and it dipped below the axis from 0 to 1. And so we have to then adjust for that to be able to do the absolute value. So the absolute value, whatever is below the axis, you flip it up to the top. How do you flip it to be positive? You put a negative in front of it. So that's why you have that negative v of t here for the portion that is below the axis, because you bring it up above the axis. And so that would be the total distance traveled. Email me if you have any questions.